In this video, we will learn signal flow graphs. Signal flow graphs provide an alternative method to block diagrams. The signal flow graph was developed by S.J. Mason. A main advantage of signal flow graphs is that a flow graph gain formula is available, and this formula is called Mason's gain formula. With this formula available, it is easy for us to find the transfer function of the signal flow graph, which represents a control system. A signal flow graph consists of a network in which nodes are connected by directed branches. And the branches have a direction which shows the signal flows. A signal flow graph illustrates signal flows of the system from one point to another. It also gives relationships among these signals. We must remember that signal flows only in one direction in any signal flow graph. Now let's look at a number of definitions that are in relation to a signal flow graph. The first one is a node. Usually, we use a circle to represent a node. So I'm drawing a number of nodes of a system. The next one is a branch. A branch is a unidirectional line segment connecting two nodes. So now I'm drawing some branches. And the branches should always have a direction. And this direction shows the flow of a signal. The third definition is a path. A path is either a branch or a continuous sequence of branches that can be traversed from one node to another. So on the signal flow graph I'm drawing, you've seen a path. The next definition is a loop. As the name suggests, a loop is a closed path which originates and terminates on the same node. And along the path, no node should be met twice. So now I can draw you a loop. So this is a loop. The last definition on the slide is non-touching loops. Two loops are said to be non-touching if they don't share a common node. So I've drawn two loops, and these two loops are non-touching because they don't have a common node. On this slide, I'm trying to give you a comparison between signal flow graphs and block diagrams. Signal flow graphs and block diagrams, they represent the same information contained in the system. The only difference between them is the way the information is represented. This block diagram, we've seen it in the last video. It represents a two-input, two-output system. If we draw the corresponding signal flow graph of the same system, it looks like this. The transfer function between signals is written in a block. So these blocks represent the transfer functions between signals. By contrast, these transfer functions, they are illustrated either above or below a line segment in the signal flow graph. You don't see any blocks. But the input-output relationship, or the transfer function, represented by a signal flow graph or a block diagram, is exactly the same. On the bottom of this slide, it shows the signal flow graph of two algebraic equations. And the two loops here, they are called self-loops. Associated with any signal flow graph is the Mason's gain formula. So the Mason's gain formula governs the derivation of the transfer function represented by a signal flow graph. Let's read the top two lines. The linear dependence Tij between the independent variable xi and a dependent variable xj is given by this formula, which is known as the Mason's gain formula. The independent variable xi is what we know as the input. And the dependent variable xj is basically the system output. And Tij is the transfer function between xi and xj. If we ignore the subscript I and the subscript j, we can simplify this formula as T equals sigma k pk delta k over delta. K is the path index, so one path at a time. And Pijk is simply pk. Pk means the kth path gain from the input to the output. And the next variable is delta. Delta is called the determinant of the graph, and there is a formula to calculate delta. So let's look at this formula. Delta is equal to 1 minus the first summation, and the explanation of the first summation is here. It is a sum of all different loop gains. Then we have a plus sign, and if you look more closely into this formula, you will see the sign actually alternates. Now let's talk about the second summation. The explanation of this summation is given by the second bracket. The sum of the gain products of all combinations of two non-touching loops. Then we have the third summation. And the explanation of the third summation is given by the information in the third bracket. It means the sum of the gain products of all combinations of three non-touching loops. So the loop gain here is represented by this capital L and depends on which loop you are looking at. We will see the example of Mason's gain formula in the next slide, and everything mentioned here will become clear. After we get delta, we need to determine delta k or delta ijk. If we ignore the subscripts, delta ijk basically is delta k. Delta k is called the cofactor of the path pk because it is associated with a path index k. So how do we determine delta K? Delta K is derived from delta. We need to remove the loops touching the kth path from delta. What is left is delta K. Because delta K is associated with the kth path, every time we have a different path, we may have a different delta K. Delta is common for all the paths, but delta K can be different from one path to another. To get the transfer function between the input and the output, we use Mason's gain formula. And the step-by-step approach is given on this slide. First, we need to look at paths, forward paths. And we look at one path at a time. We need to calculate the forward path gain for each available path in the signal flow graph. The second step is we need to calculate all the loop gains or the loop transfer functions. A signal flow graph may contain a number of loops, so we need to calculate each loop transfer function. The third step is we need to identify non-touching loops. First, we look at 2 non-touching loops. Then we look at 3 non-touching loops. With the information of loop gains and 2 non-touching loops and 3 non-touching loops and so on, we should be able to calculate delta. And with availability of delta, we can calculate delta K, because delta K is a portion of delta with the loops touching the kth path removed. It's better to look at an example. In this example, we say 2 paths between the input and the output. And these 2 paths, if you follow my pointer, this is what we call path P1. We also have a second path to go from input to the output. And the second path is this path, and we call it P2. So first you need to calculate all of the path gains. In this case, you need to calculate P1 and you need to calculate P2. So the path gain basically is a product of the individual transfer functions along the path. After that, you need to concentrate on loops. In this example, you can see 4 loops. 2 loops on the top and the other 2 loops on the bottom. And they are represented by L1, L2, L3, L4. You need to find all of the loop transfer functions. So that is given by this step. After that, you need to identify whether your signal flow graph contains any non-touching loops. And you need to look at 2 non-touching loops at a time. Then you move on to 3 non-touching loops, if any. In this example, we can see that this signal flow graph only contains some 2 non-touching loops. Because loop 1, which is L1, it does not touch loop 3 and it does not touch loop 4. Loop L2 does not touch L3, it doesn't touch L4 either. So these are two non-touching loops. Then you need to ascertain whether your signal flow graph contains any 3 non-touching loops. In this example, there are no 3 non-touching loops. With the information in steps 1, 2, 3, 4, you should be able to calculate delta. Delta is given by the formula which was shown in the previous slide. So the first term in delta is always unity 1. Then you have a minus sign to go after it. And then you have the first bracket. The first bracket should give you the sum of different loop gains. Then you have the plus sign. After that, you have the second bracket in which you should calculate the sum of the gain products of all the combinations of 2 non-touching loops. That is this. After you calculated delta, you should be able to calculate delta K. Delta K goes with path K. So in this case, we have K equals 1 and K equals 2. So K equals 1 means you look at the first path. And when you look at the first path, delta 1 should be part of the delta with the loops touching the first path removed. Therefore, any loops touching the first path should be removed from delta. What is left is delta 1. In this case, delta 1 is obtained as this. Same for delta 2. Delta 2 means you look at the second path, and any loops touching the second path should be removed from delta. What is left is delta 2. After you calculated P1, P2, delta, delta 1, and delta 2, you should assemble them to find the transfer function of this signal flow graph. Now let's look at another example. And in this example, I've shown you both the block diagram and the signal flow graph. And this example is an armature-controlled DC motor. So in the top graph is the block diagram of this system. And the armature transfer function is given by G1. And the load transfer function is given by G2. Of course, G1 and G2 mean G1S and G2S. I have omitted S for simplicity. From the block diagram, you can see that to obtain the transfer function, theta S over VAS, what we need to do is just to delete this loop. So we need to remove this loop. And you may ask me, there's also this disturbance signal or disturbance input. Do we need to care about that? And the answer is no, because according to the superposition law, the inputs to a linear system can be considered independently. And the transfer function we are after here is the transfer function between the reference input and the system output. That is theta S over VAS. When we look at the transfer function theta S over VAS, we don't have to worry about the existence of the disturbance signal, TDS. So that's how we derive the transfer function for this block diagram. And if we use the signal flow graph to represent the same system, it is shown by the bottom graph. So how do we use Mason's gain formula to find the transfer function of this system? We just need to find the information about the path gain, about the loops, and we need to find delta and delta k. In this case, there's only one path. Therefore, we only need to find P1. And there's only one loop, which is this loop. So we just need to find L1. So this is the loop transfer function. And delta is calculated by 1 minus the first bracket, and in the bracket, it should contain the sum of different loop gains. And in this case, we only have one loop, therefore delta is equal to 1 minus L1. After that, we should look at delta 1. Delta 1 is a portion of delta with the loops touching the first path removed. Since we only have one loop, and this loop does touch the first path, the only thing left in delta is unity 1. After we find all this information, we just need to assemble them to obtain the transfer function theta s over VAS. Let's look at one more example. This example is what we have seen in the last video. This is a multi-loop feedback control system. Now we use Mason's gain formula to find the transfer function, and we should compare whether the result is exactly the same as the previous one. So the first step, we need to find forward paths. And in this example, there's only one path, and this is a horizontal path, which is given by P1. Now, let's look at the loops. Obviously, in this example, it has 3 loops. So we need to calculate all of the loop transfer functions. After we find L1, L2, and L3, we need to identify whether there are 2 non-touching loops. And in this system, all the 3 loops touch each other. With this information, we should be able to determine delta. So delta is equal to 1 minus bracket L1 plus L2 plus L3. And then we should calculate delta k. In this case, there's only one path. Therefore, we should only calculate delta 1. And we can say all the 3 loops touch the forward path in this example. Therefore, everything should be removed from delta except unity 1. So delta 1 is equal to 1. After we get P1, delta, and delta 1, we assemble them to find the final solution of the transfer function Ys over Rs for this multi-loop feedback control system. Now let's have a summary of block diagrams and signal flow graphs. These 2 graphical models illustrate the relationship between system variables. For block diagrams, the simplification procedure can be cumbersome for a complex system. In contrast, Mason's gain formula is useful when handling large and complex systems. However, when we make a mistake in using the Mason's gain formula, the mistake may not be easily detected.